Hey, welcome back. In this video, we're going to start discussing probabilistic methods, and we'll apply them to a few problems about graphs. So far in this course, we've seen a bunch of tools for proving bounds on extremal problems about graphs. One of the most popular tools for these kind of problems is induction. We've also seen a bunch of the inequalities apply to these problems, including the trivial inequality, the Cauchy-Schwarz inequality, Jensen's inequality, which can be used to prove most of these other inequalities, AMGM, the arithmetic mean geometric mean inequality, and power mean inequality. So we proved that one. We haven't seen power mean applied to any problems yet, but we will see it at some point. All the others, though, we've seen applied to at least some problems. In this video, like I said, we're going to start discussing probabilistic methods. We'll only see a few methods in this video, just to get an introduction to probabilistic methods in general. And the specific problems that we'll look at in graph theory are problems about coloring hypergraphs, splitting graphs up into bipartite graphs, and finding lower bounds on the Turan extremal functions of complete bipartite graphs. Before we get to any proofs, let's define some terminology about hypergraphs. So first, we're going to generalize the notion of graphs that we looked at before, and we're going to say a k-uniform hypergraph is a pair v comma e, just like we saw with graphs, where v is the set of vertices, and e is the set of edges, and e is a set of subsets of v of size k. So in the case that k equals 2, we have two uniform hypergraphs. These are just the graphs that we've been talking about in the past videos. Here's another term. We say that a hypergraph is x colorable if its vertices can be colored with x colors so that at least two different colors appear on every edge. In other words, the vertices can be colored with x colors so that there is no edge in which all vertices have the same color. So given this notion of x colorability, we can define an extremal function, m of k, to be the minimum possible number of edges in a k-uniform hypergraph that is not too colorable. And this is a pretty big open problem to find m of k in general. It's known for some small values of k. So when k equals 2, again, two uniform hypergraphs are graphs. So the problem when k equals 2 is to find the minimum possible number of edges in a graph that is not too colorable. And we can see that the smallest number of edges in a graph that's not too colorable occurs when we have a triangle. So we get 3 for k equals 2. And it's also known that m of 3 equals 7. For higher values of k, there are some pretty good bounds on m of k. So it's known that m of k is pretty close to 2 to the k, but it has an extra factor that depends on k that grows much more slowly than 2 to the k. In this video, we're going to prove a lower bound on m of k of 2 to the k minus 1. And we're going to use a tool from probability called the union bound. And the union bound says that if we have a bunch of events, the probability of their union is at most the sum of their probabilities. So we want to prove that the minimum possible number of edges in a k-uniform hypergraph that is not too colorable is at least 2 to the k minus 1. So we can consider a k-uniform hypergraph with fewer edges than that. So we can say H is an arbitrary k-uniform hypergraph with fewer than 2 to the k minus 1 edges, and it suffices to show that H is too colorable. Because if we can show that H, an arbitrary k-uniform hypergraph with fewer than 2 to the k minus 1 edges, is too colorable, that means that any k-uniform hypergraph with fewer than 2 to the k minus 1 edges is too colorable. And that would imply then that the minimum possible number of edges in a k-uniform hypergraph that is not too colorable would have to be at least 2 to the k minus 1. So that's why we're going to try to prove this. So we're going to try to find some coloring of H, a 2 coloring specifically. And in order to do that, we can use an experiment. So we'll use some randomness. We will independently color each vertex of H red or blue, each with probability 1/2. So we'll flip a coin to decide for each vertex of H, are we going to color it red or blue? Now, we can look at any edge E and H, and we can note that the probability that all of the vertices of E are the same color is 1/2 to the k minus 1. Let's see why that's true. So let's say x of E right here is the event that all vertices in E are same color. So probability of x of E equals the probability that E is all red plus the probability that E is all blue. So if all of the vertices in E are the same color, either they're all red or they're all blue. And it's impossible for them both to be all red and all blue. So the probability that all of them are the same color is going to be the sum of the probabilities that they're red and the probabilities that they're blue. And we want to find the probability that all the edges, all the vertices in the edge E are red. Well, we can note that each edge in the k-uniform hypergraph has k vertices. Each vertex gets colored red with probability 1/2. So the probability that all of the vertices in this specific edge E are red is just 1/2 to the k. And we get the same value for the probability that all of the vertices in E are blue. We get 1/2 to the k. Because there's a 1/2 probability that each of those vertices are blue, and all of them are colored independently. And when we add these two probabilities together, 1/2 to the k plus 1/2 to the k, we get 1/2 to the k minus 1. So that's how we can conclude that part. And on the next line, we can see that based on our assumption that H has fewer than 2 to the k minus 1 edges, we can get a bound less than 1 on the probability that there exists an edge in H in which all of the vertices are the same color. So let's see, why is that true? So this probability that there exists an edge in which all the vertices are the same color, that's the probability of the union of the xe's. So the union over all the edges in H. So all the edges in its edge set E of the event xe. So that's the probability that there exists an edge in which all vertices are the same color. By the union bound, this is going to be less than or equal to the sum over the edges of the probability of xe. And we got in the previous bullet that probability. So that probability was 1/2 to the k minus 1. And here's where we can use the fact that H has fewer than 2 to the k minus 1 edges. We can say that this is going to be less than 2 to the k minus 1 2 to the k minus 1 up here divided by 2 to the k minus 1. So how do we get that? Well, we had a bunch of 1/2 to the k minus 1s from here, from right here. How many of those 1/2 to the k minus 1s do we have? Well, we have the number of edges, and the number of edges is less than 2 to the k minus 1. So we get a number that's less than 2 to the k minus 1 over 2 to the k minus 1. This equals 1. So we see now that the probability that there exists an edge in which all the vertices are the same color is strictly less than 1, strictly because this less than right here. and that follows because we have fewer than 2 to the k minus 1 edges. And now we're able to finish it off. So since we know that the probability that there exists an edge in which all the vertices are the same color is less than 1, that means that with non-zero probability, none of the edges have all of the vertices of the same color. In other words, all the edges have at least 2 different colors that occur with non-zero probability. So since we just showed with non-zero probability, at least 2 different colors appear on every edge, that means that there must exist some 2 coloring of H in which at least 2 different colors appear on every edge. And that implies, by definition, that H is 2 colorable. So notice we didn't find the 2 coloring. All we did is show that it must exist, just using probability. So now let's look at another tool. And this tool is just expectation, expected value. So on the previous slide, we used the union bound, and that gave us a pretty sharp bound on m of k, because we got a lower bound of 2 to the k minus 1, and we saw that in general, the m of k has upper and lower bounds, which give a bound of 2 to the k times 1 plus little o of 1. So the lower bound that we proved is not too far from the best known upper bound. Now, the tool that we're going to see on this slide is a little different. We're going to use expected value to prove some bounds. And the bounds that we're going to look at here are bounds about splitting graphs into bipartite graphs. And when we use expectation, often when we use it for combinatorial problems where we're using probabilistic methods, when we use the expectation, we're going to be using linearity of expectation. What does that say? Well, it says if you have a bunch of random variables, which we will call x1, x2 up to xk, the expectation of the sum of the xi's is equal to the sum of the expectations of the xi's. So here's an example problem where we can use expectation to get a bound. So the question is, why does every graph with m edges contain a bipartite subgraph with at least m over 2 edges? So we're going to prove this, again doing an experiment involving randomness, but this time we'll use expected values. So we're going to start with an arbitrary graph G, and it's going to have m edges. And we're going to have to show that G contains a bipartite subgraph with at least m over 2 edges. We'll assume the vertex set of G is V and the edge set is E. We're going to choose a random subset, we'll call it T, of the vertices V, and each element of T will be chosen from V with probability 1/2. So every vertex from V will be independently inserted into T with probability 1/2. Now we're going to define a random variable x, and x will just be the number of edges having exactly 1 vertex in T. We're also going to define a bunch of other random variables, which we'll call indicator random variables. It's not really important to know this term. All you need to know here is the definition of these random variables. And these random variables, xe, will be defined to be 1 if exactly one of the vertices in the edge E is in this set T that we formed 2 bullets ago, the random subset T, and xe is 0 otherwise. And E is some edge in the edge set E. So E has 2 vertices in it. Those vertices would be U and V for some U and V. And so xe is going to be 1 if exactly 1 of U or V is in T, and 0 if neither U or V is in T, or both U and V are in T. Now, we can observe something. We can see that the random variable defined 2 bullets ago the random variable x right here, x is going to be the sum over the edges, little e and big E, of these indicator random variables, the xe's. So x is just counting the total number of edges having exactly one vertex in T. These indicator random variables xe are going to contribute 1 to x if the edge E has exactly one vertex in T, and they'll contribute 0 otherwise. So this sum of the xe's actually is giving us exactly what we're trying to count for x. So that's why x is equal to the sum over the edges E of the xe's. And here, we can use the linearity of expectation. So linearity of expectation, we can apply that down here. And we're going to apply it knowing the fact that each of the xe's is going to have an expectation of 1/2. And we should probably look at that for a second. So the expectation of xe being 1/2. Why is this true? Well, the random variable has value 1 if exactly one of the vertices of E is in T and 0 otherwise. So we can look at U and V. And the possibilities are that they are both in T, U is in T, and V is not in T. U is not in T, and V is in T. Or they're both not in T. Now, the value of xe, if they're both in T, it will be 0. If U is in T but V is not, it'll be 1. If U is not in T but V is in T, it'll be 1. And if they're both not in T, it'll be 0. Each of these events over here for U and V happen with probability 1/4. So the probability that both U and V are in T is in 1/4. The probability that only U is in T is 1/4. The probability that only V is in T is 1/4. And the probability that neither one of them is in T is 1/4. So our expectation of xe is going to be 1/4 times 0 plus 1/4 times 1 plus 1/4 times 1 plus 1/4 times 0. So that's how we get the 1/2 there. Okay, and now we can apply the linearity of expectation, like I said. So we can say that this sum is equal to the sum over E and E. So expectation of x is going to be the sum of the expectations of the xe's. So it's just going to be the number of edges times 1/2. And we can see that in the last bullet. So we get that the expectation of x is just the number of edges times 1/2, and that's exactly m/2. So we saw that when we performed this experiment, the expected number of edges having exactly one vertex in T is equal to m/2. And this gives us exactly the bipartite graph that we're looking for. So by definition, since the expected value is m/2, there must exist some choice of T as a subset of V such that there are at least m/2 edges from T to V minus T. And those m/2 edges give us the subgraph that we're looking for. And that's the whole proof. And I'll note that that subgraph is bipartite because all of its edges are going from one part to another. The one part is T, the other part is V minus T. So here's a problem for you to think about, which uses similar methods to what we've looked at so far. So the question is what is the expected number of fixed points of a random permutation of 1, 2, up to n. And we've seen fixed points before in earlier videos. And same idea here. Okay, so we're going to look at one last tool in this video, but we'll definitely look at more tools in future videos related to the probabilistic methods. So this last tool we're going to look at is called an alteration. So the tools that we looked at so far, the union bound and expectation, we use those both to get bounds on these problems about graphs, these extremal problems. And these tools, the way they worked is we did an experiment. So we randomly built some structure. And when we used both these tools, we saw that typically the structure that we built had the properties we're looking for. Typically, I mean like with high enough probability, the structure had the properties we're looking for. So we're able to just say the structure that we're looking for exists. Now, sometimes we'll perform the experiments, and when we randomly build the structure, it will not usually have the properties that we're looking for. So like we won't be able to necessarily say with high enough probability, like with probability greater than 0, that there's a structure with the properties that we're looking for until we do something to the structure that we built experimentally. So maybe the original experiment doesn't produce the kind of structure that we're looking for, but if we modify it just a little bit, we can get a structure exactly with the properties that we want. So that's the basic idea of doing alterations, is we'll do an original experiment and then we'll modify it a little bit to get the structure that we're looking for, or I should say a structure that we're looking for. And the key will be that the modification that we do will not change the size of the structure too much. So if it's a problem where we're trying to maximize the number of edges in a graph with some property, our modification is not going to get rid of too many edges. And like I said, that's the basic idea of the alteration method. And we're going to apply this to a problem. And this problem is a problem that we've been looking at a bunch in this class. And that is Turan extremal functions. So just to review, we say that the graph G contains the graph H if some subgraph of G is isomorphic to H. And we call G H-free if G does not contain H. And we define this Turan extremal function, Ex of n comma H, to be the maximum possible number of edges in an H-free graph of order n. And in an earlier video, using Jensen's inequality, we proved that the extremal function of n comma KRS, in other words, the complete bipartite graph with parts of size R and S, it has an upper bound, that Turan extremal function, of big O of n to the 2 minus 1 over S. And this is true for all R greater than or equal to S greater than or equal to 2. And we can look specifically at the diagonal case of the complete bipartite graphs, so when the parts have equal size. So that last bound in the last bullet tells us that the extremal function of n comma KSS is big O of n to the 2 minus 1 over S. And it's natural to ask for lower bounds on this. And like I mentioned in that earlier video, lower bounds are known, which are on the same order of magnitude as the upper bounds, in the case that S equals 2 and S equals 3. And we'll see some more information about that in a future video. In general, though, this is a major open problem to see whether or not these upper bounds are sharp up to a constant factor. And the lower bounds that are known for this problem, this Turan extremal function, are not within a constant factor of the upper bounds for all S greater than or equal to 4. So we're going to prove the best known general lower bound for this Turan extremal function of complete bipartite graphs of equal sizes. And this is the best known general lower bound up to a constant factor. And we're going to use probabilistic methods for this. Specifically, we'll use alterations. So we're going to start out by saying that P is greater than 0 and it's some constant, and we're going to choose it at the end of the proof. So we're going to do this proof in terms of p, and then at the end, we will choose p so that things work out. So first step in our experiment is we have n vertices, and we're going to randomly choose a graph on those vertices by including each possible edge with probability p. And remember, p is this constant from the first bullet that we haven't said what it is yet. We're going to choose it at the end of the proof to make everything work out. Now, we can see that the expected number of copies of the complete bipartite graph KSS in G is going to be n choose 2s times 2s choose s times p to the s squared. Now, why is that? Well, the number of ways to choose 2s vertices for the possible copy of KSS. That's the n choose 2s. Number of ways to choose the parts once we've chosen the 2s vertices in the graph. That's how we get the 2s choose s. So that's the number of ways to choose the left part, and then that gives us the right part as the remaining s vertices out of the 2s. And then the p to the s squared. What's that from? Well, we can think of the expected numbers of KSS and G. We can say x is the random variable for the number of copies of KSS in G. And we can say for each possible copy, and we'll call it, let's say, y, we'll define x sub y to be 1 if it is a copy, and 0 otherwise. And let's explain a little more what we mean if it is a copy. So if it is a copy, it means that if all edges are present between the parts. So between the two parts we chose with sizes s each, if all edges are present between the parts, so when we did the experiment to construct our graph, if all edges are present between these two parts in this possible copy, and this possible copy is just a set of 2s vertices with s of them denoted left and s of them denoted right. So if all of the edges are present between the parts, then this random variable x sub y will be 1, it'll be 0 otherwise. And the thing that we can note here is that x, the random variable up here, this x, is equal to the sum over all the possible copies y of x sub y. And now, if we want to find the expectation of x, all we have to do is find the expectation of xy and add them all up. And the expectation of x sub y, so the expectation of x sub y is going to be the probability that all of the edges are present between the parts times 1 plus the probability that not all of the edges are present between the parts times 0. So first, let's look at the probability that all of the edges are present between the parts. So if we have two parts, each size s, the number of edges is going to be s squared. Each edge is present with probability p. So each edge was included with probability p. So the probability that all the edges are present is going to be p to the s squared. And then if we want to find the expectation of x sub y, we're multiplying that probability times 1. So that gives us probability that all the edges are present times the value of x sub y when all the edges are present, plus the probability that not all of the edges are present, so 1 minus p to the s squared, times the value of x sub y when not all of the edges are present, which is 0. So that second term doesn't matter, it gets zeroed out. And we get p to the s squared here. So we can substitute that p to the s squared in the sum down here. So we get the sum over these y of p to the s squared. And these y, each y gives us the same expectation for the, so we're taking expectation here. I didn't write my expectations, sorry about that. So we write our expectations there. And we can use linear expectation, so I'll put an extra step there to write this as the expectation of the x, y's summed up. And that gives us the sum over y of the p to the s squareds. And we saw that the number of possible copies, so for each possible copy, we counted the number of possible copies over here. So the number of ways to choose 2s vertices for the possible copy was n choose s. The number of ways to choose the parts from there is 2s choose s. So that gives us the total possible number of copies is just going to be n choose 2s times 2s choose s times p to the s squared. And that's exactly what we got right here. So it's a little more explanation than is in that bullet. Okay, so we're about halfway there, I guess. Let's clear up that so we have some more room. Now we're going to do the alteration. So we don't want to have any of those copies of KSS. We want to build a graph that is KSS free. So what we'll do is in each copy of the KSS, we'll just delete one edge. And the claim is that the expected number of edges in the resulting graph is at least n choose 2 times p minus n choose 2s times 2s choose s times p to the s squared. Let's talk about that for a second. So this part right here, you probably recognize it. It's exactly what we saw up here. So when we take out one edge from each of the copies of KSS, we're going to remove at most this many edges. It's possible that we'll remove fewer edges than this. That's because it's possible some of the copies of KSS have overlapping edges. So if we remove an edge where they overlap, we can use one edge to get rid of two copies. And it could be two or more copies. So if there are some overlapping edges, we can use one edge to get rid of multiple copies. So this part is the edges that we cut out, the part that I put in the box. This part right here, this is just going to be the expectation of the number of edges in G. So not the number of edges in the graph we got from altering G, but the expectation of the number of edges in G. So G has a total of n choose 2 possible edges, because G is a graph of order n, but each edge was included with probability p. So the expectation of the number of edges in G, we can say that we can do something similar that we've done in the previous problems. We can say x is the random variable for the number of edges in G. And we can define indicators. So we can say for each E in our edge set of G, we can define XE will be 1. So we can actually make this, instead of E in the edge set E, we can make that for any possible E. So for all possible e, we'll define xe equals 1 if e was chosen to be in our graph, so if e is in e, and 0 otherwise. And so the number of possible e is just n choose 2. So any possible subset of true vertices in our graph is a possible edge. Now, the probability that each edge gets included in our graph is p. So the expectation of xe is just going to be p times 1 plus 1 minus p times 0. And so we get that this expectation here, the expectation of the number of edges in G, that's equal to expectation of x. That's equal to the expectation of the sum over all the possible edges of E of xe. We can use our linear of expectation to write that as the sum over E of the expectation of xe. And then we can use the fact that we calculated expectation of xe up here. It's just p because the other term zeroes out. So we get sum over E of p. And again, the E is being summed over the possible edges. So there's n choose 2 possible edges because there's n vertices. So we get n choose 2 times p. So that's how we got that first term, the n choose 2 times p. And the term that's being subtracted, we already explained how we got that. So when we do this alteration, the expected number of edges in the graph that we get is at least n choose 2 times p minus this quantity, the n choose 2s times 2s choose s times p to the s squared. Now we're real close to the end of it. So here's a problem that I leave you to think about. I claim that if we choose a p-value less than or equal to n to the negative 2 over s plus 1, then we get n choose 2 times p minus n choose 2s times 2s choose s times p to the s squared is greater than or equal to 1/2 times n choose 2 times p. So notice here that we have an n choose 2 times p here, and we have a 1/2 times n choose 2 times p here. So the claim is equivalent to saying that this thing right here, this quantity, is at most 1/2 times n choose 2 times p. In other words, this quantity right here is at most half of this quantity. So see if you can prove that, assuming that p is in this range. And the claim then is that assuming that that problem is true, we get this lower bound of ex of n comma kss is big omega of n to the 2 minus 2 over s plus 1. And why is that? Well, we can look at that for a second. So we just showed that the expected number of edges is at least 1/2 times n choose 2 times p. And that's if we choose p less than or equal to n to the minus 2 over s plus 1. And if the expected number of edges is at least this, then that means that there is a choice of graph G on those n vertices for which the number of edges is at least this. So the number of edges is going to be greater than or equal to this. Now, the graph we constructed is KSS free. So the altered graph is KSS free. We got rid of every copy of KSS by deleting an edge from it. So the altered graph is KSS free, and its number of edges is greater than or equal to 1/2 times n choose 2 times p. Since this inequality right here in the problem is true for any p less than or equal to n to the minus 2 over s plus 1, we can take p as large as possible in order for it to be true. So we'll take p equal to n to the minus 2 over s plus 1. And when if p right there, if we set it equal to n to the, so p equals n to the minus 2 over s plus 1, then we can see that this just equals 1/2 times n choose 2 times n to the minus 2 over s plus 1. And the 1/2 n choose 2, this one is clearly big omega of n squared. So 1/2 n choose 2 is big omega of n squared. And we're multiplying that by n to the minus 2 over s plus 1. So we're getting big omega of n squared times n to the minus 2 over s plus 1. So we're getting n to the 2 minus 2 over s plus 1, big omega of that. And we can say that this is a lower bound on ex, the Turan extremal function of the complete bipartite graph with parts of size s, because the graph that we constructed is KSS free. So we just showed that lower bound of omega of n to the 2 minus 2 over s plus 1, and all we used was the simple probabilistic method with the alteration. And just as a reminder, we also proved this upper bound in the previous video, this upper bound in the next bullet of big O of n to the 2 minus 1 over s. We proved that upper bound with Jensen's inequality. So you can see for s greater than or equal to 4, these are the best bounds that are known and they're far apart. For s equals 4, there's actually a better bound that's known than this. So when s equals 4, the lower bound that we get here, so this lower bound, when s equals 4, so it gives us ex and k44 equals omega of n to the 2 minus 2/5. And we can also say that ex of n k44 is greater than or equal to ex n k33, because k44 contains k33, and this equals omega of n to the 2 minus 1/3. And 2 minus 1/3 is greater than or equal to 2 minus 2/5. So that gives a slightly better lower bound for the case that s equals 4 is just using the lower bound that's known for k of 3,3. But for higher values of s, this actually is the best lower bound that's known. So s greater than or equal to 5, that gives you the best lower bound. And you can see that that is pretty far from the upper bound. So it's not within a constant factor of the upper bound. So that's a big open problem, is to try to sharpen those bounds and figure out what is the order of the bounds, the correct order in terms of n. So that brings us to the end of the video. Thanks for watching. Oh, wait, another problem for you. And then we'll be at the end. So the problem is to prove that if G has order n and m edges and average degree d, then the largest independent set in G has size big omega of n over d. So see if you can prove that, maybe using alterations, and you're also welcome to use any other things that we proved in class. So this result has multiple proofs. There might be a proof that doesn't use the probabilistic method at all. We'll see. So I think that is actually the end of the video. So thanks for watching.